Bonjour, my name is Antti Pakonen and I work at VTT. Function block diagrams, like the one you see here, are a common specification or programming language for INC logics. But the problem is that given sufficient complexity, you cannot rely just on testing to prove that the design is 100% correct. Model checking is a formal verification method where the objective is mathematical proof of correctness. You take the design you are verifying and construct a model of it, as you would do in simulation. You then take the functional requirements targeted at the system and express those requirements as formal properties. This allows you to use a computer tool called a model checker to prove that either your model satisfies these properties or there is a counterexample revealing either a mistake that the analyst made in modeling, which is then fixed, or a potential design issue in the design being verified. And this analysis is exhaustive, meaning that it covers all the relevant states and executions of the system model. The properties can address the expected behavior of the system, but also the so-called negative requirements, like never trip unless the trip criteria are set. In other words, never spuriously actuate. In Finland, INC model checking is an industry practice. We have used it in new build projects and INC renewal projects. We have used it to check early functional design and final detailed INC design. We have used it to check microprocessor and FPGA logics. In every major project in Finland having to do with digital INC, for over a decade now, we have successfully used these methods. In these projects, we have revealed a total of 75 design issues, confirmed to be real issues by the people who designed the logics. Almost a third of them feature spurious actuation, which underlines how difficult it is to otherwise find such errors. The counterexamples often involve unlikely scenarios that were not covered in testing, like the operators or the maintenance personnel misbehaving, different unrelated signals coming in at the exact same PLC cycle, or input data from the measurements acting crazy. In model checking, the analyst does not have to come up with these scenarios. It suffices to formalize a property like never spuriously actuate, and if a counterexample is possible, however unlikely, the model checker will find it. In the words of our regulator, model checking is a very effective method. The utilities here think that it's truly beneficial. It finds issues that otherwise would not have been found, and the results are so remarkable that it's worth it to also check systems of a lower safety class. With those customer statements in mind, I'd be happy to discuss how to put this stuff into broader use. Merci.
Until now, in a nuclear power plant, any operator wishing to train had to do so in the simulation room, a replica of the control room. A full-size simulator was the only choice and is not easy. To that end, some partners in the French nuclear industry have been working together to develop, by 2023, an ergonomic, easy-to-use and accessible solution, the digital reactor. So what is it? The digital reactor is the digital twin of an existing reactor coupled with real site data. It is a faithful representation of the reactor following its life cycle from design to decommissioning, along with all its specificities and modifications throughout operation. With the digital reactor, control teams can simulate situations as close as possible to the real scene and thus explore, visualize, anticipate maintenance interventions, and understand the reactor physics in any operating situation in an instant. And it can all be done remotely. The digital reactor will be used as an online training simulator, a complement to the training of the operators currently ensured by trainers. This educational tool is composed of a representation of the main commands of a control room, coupled with an advanced 3D visualization of the physics phenomena occurring within the reactor. Our priority use cases are the sensitive operating situations rarely carried out during an operator's life. The expected benefits for the users of our product are improving the operating performance through the reduction of non-quality operation, bringing serenity to operators in the context of the preparation of a sensitive activity. The 3D visualization tool will enable the operators to better apprehend the processes to carry out during operation with a high-fidelity representation. A first prototype was specified in 2020 and developed in 2021. It was evaluated by operators during the first half of 2022. Consequently to the result of the assessment, the product would be deployed as an experimentation in French nuclear power plants during the first half of 2023.
Hello everyone, today we're going to present the innovation project Parametric Virtual Model that is developed between the Assystem teams. The aim of this project is to design a digital and parametric environment to support the activities throughout the life cycle of an SMR power plant. We focused on the first phase on the design of SMR. The aim is to have a standard specification of an SMR and apply specific requirement for a specific site, for a specific client, and obtain a specification that is compliant with all the input requirements. How it works, so a user enters the site parameters, the requirements, and it is entered in a database that already includes different architectural models, different functions, and a components catalog of an SMR. And all of this is used by an optimizer to design different architectures and designs of an SMR that are simulated and then evaluated against the input requirement. And this cycle is repeated until the result is satisfactory. We built a proof of concept on a reduced scope. So it's a condenser and a cooling tower. So the aim for the PVM is to choose the best condenser and the best cooling tower to fulfill the performance requirement we entered. So this is based on different inputs, so a Capella model that we built, different parameters of input temperature, output temperature, and a component catalog. And additionally, a behavioral modeling library that we use to simulate the different design generated.
So here is an overview of the input data that we have used in the PVM for the proof of concept. So here's a set of requirements that were formalized with some specific objectives, weights, values, and tolerance. We had also a catalog of components from which we're going to choose one system for each parameter, for the cooling system, conveying system, and also the condensing system with different parameters. And we have also built a Capella model in which we have our design patterns, which are different functions of different subsystems of our concept. We have also a structure of our model that will constrain the relationships between the different elements of our architecture. And finally, we have the exchange items that specify the flows that we have between the different systems. So our optimizer that we have developed allowed us to generate a set of design alternatives. So these are different architectures with a different number of subsystems. For example, we have different number of cooling systems, of cooling towers, etc. And we have also we have developed an interface that allows us to show the chosen architecture that has the best score regarding the evaluation that was made regarding the different requirements and objectives that were defined earlier. And the evaluation was made by using behavioral models. So here we have used a tool called OpenModelica with a Modelica language behind it that allows us to simulate the behavior of our system. Today, we have created these models manually, but our aim is to develop an automatic generator for this kind of models that will, from the one side, generate these models, and from the other side, it will capture the results and transform them in such a way that it would be compatible with the environment, and we can use these data for the evaluation of our system. Thank you for your attention.
Hello, my name is Florent Vezeri. I work for our system, and I am INC technical leader. I'm going to present a data review software and Proteus that has been developed by our system to support our various activities relating to the EPR project. So on the left side of the screen, you have a few supporting slides I will be using to introduce the talk, and I will be demoing the software here on the right. The main objective of Proteus is to review the quality of the EPR design data. These data are associated to many disciplines and technical fields, and two main questions that we ask ourselves is, are they consistent and do they comply with the engineering rules? The software goal is to answer these questions as extensively and as quickly as possible. So we started to work on Proteus in 2013. The user base grew until it became de facto part of the HPC INC design sequence. And at this point, Advanced decided to acquire the software. So I'm going to give you an overview, a typical use case. As a quality engineer, I want to check that the functional integration of the safety requirements with the INC and the mechanical design is correct. Doing that manually would take a lot of time, and only a few data points would be verified. But here we strive to check an entire data set. So with Proteus, we will be able to check the proper traceability of the requirements and the consistency of the data between the disciplines. So for that, I am going to use a very simple example with a safety function that we can imagine is related to the emergency water supply of a steam generator. So at the requirement level, we have a single sensor whose threshold triggers the actuation of a pump. The design sequence is as follows. So we have these requirements at the top, and downstream we have the mechanical sequence and the INC sequence. I have created a sample dataset for the purpose of the demo, and I have introduced various issues within this sample of data, and we will see with the software that we are able to find these issues, these mistakes quickly and efficiently. So in the software, the first step is to import the data generated by the project. So here I have created the demo version of the HPC project, and I have imported, for instance, the INC specifications. What I want to do is to check a plant system design to see if there are inconsistencies. So I will select the demo plant system, and I will request the software to analyze it. The results are generated as an Excel file, and I'm going to highlight the key elements found by the software. So here we have a synthesis of the remark and the discrepancies detected by the software. The main point is related to the traceability of the requirements. So here we have the safety function and the components that are involved in it. The sensor number 1 is the one that is expected to be used because it is mentioned in the requirements, but in the design, in the specifications, I used instead sensor number 2, and the software correctly indicates that there is an issue because it expected a sensor, the one from the requirement, and it was not found in the specifications. Whereas for the pump, I used the correct pump in the specification, and so matching the design with the requirements is correct. Then the second question is to determine if the INC design is consistent with the mechanical design. And for that, I will be going to another tab, this one. And in this tab, we can see a comparison of the parameters that are shared between the mechanical and the INC design. And here we can see that the pump has several issues because in the mechanical design, it is expected or stated, perhaps, that the behavior upon loss of control voltage is fail-safe, whereas in the INC design, I specified that the behavior is to maintain the state. And so, as you can see, for this brief example, we are able, with Proteus, to find out quickly if there are inconsistencies or flaws in the design, and we are able to assess the quality of the data and the traceability of the requirements. Feel free to contact us if you want further information.